and different sizes of beam that will accommodate the load. So we have to examine the moment within the beam and the shear force within the beam. So that's the purpose of what we're doing. When we look at this simple diagram here, we have on the left hand side here, we have what we call a pin or hinge support. We then have a UDL, we have a point load, and then we have a roller support. UDL means uniformly distributed load. With the supports that we have here, they could be a representation of walls or so, and you notice the symbols for these supports are different. The symbols are different. This one is called a pin or hinge, and it is represented by a horizontal and vertical reactant force. Horizontal and vertical reactant force. We'll see that right away. For the right hand side, the roller support, this is unique in its nature. The roller support is represented by one force, one reactant force, perpendicular to the base of it. So if this was oriented in the vertical direction where the roller was over here, you would have a force acting that way. So it's perpendicular to the base of it. The first thing that I have to do is place some guidelines here, because we're going to have a stack of diagrams. The next diagram is dependent on the previous diagram. Say for instance, if I didn't have a beam diagram, I couldn't construct a free body diagram, which you'll see right away. Okay, we put a guideline at each location where you have a change of loading. We have right at this left hand side, we have the end of the beam, and usually you put a guideline at that location. We also have a reactant force or two reactant force right there. So we're going to place a guideline. The end of the uniformly distributed load, I'm going to put a guideline, and the point load guideline, and on the right hand side where we have the reactant force for By, we're going to have a guideline there. These guidelines are here because we're going to place a stack of diagrams. Stack of them. First one that's going to happen is a free body diagram, and if we didn't have, again, the simple beam here, we couldn't construct a free body diagram. So the next diagram is dependent on the previous diagram, and after the free body diagram we're going to do a deflected shape, and we're going to do a little bit of an explanation there. We're going to do a load diagram, we're going to do shear force diagram, and then finally a bending moment diagram. And the shear force diagram, the maximum deviation, we're going to pick that number of, and same with the bending moment diagram. So let's go and create our FBD. Free body diagram means that you have cut a part of a structure away from the original structure, and you have replaced the supports with forces. In this case, the supports are a pin support and a roller support. Pin support is associated with two forces, one horizontal, one vertical. Roller support, in this case, it is one vertical force, By. With the requirements of an FBD, you're drawing it with a straight edge. You have to have all of the loading involved. If you don't have magnitudes, you're going to label them. You're going to have dimension. Well, I'm not going to repeat the dimensions because they're right up here, and that's one of the reasons for stacking the diagrams too. You don't have to repeat certain types of information. They're right there. Okay, so I have my dimensions in here. I have all of my magnitudes that I need. If you notice for AX, which is this reactant force right there, I already have a magnitude of 0. The reason for this is that we don't have any horizontal component to cause a reaction. From this particular support. Okay, if we had an angular force, then the component would cause a reaction. We would have a magnitude other than 0 for this. Okay, the next thing to do is to go and calculate the magnitude of AY and BY. We have to calculate the magnitude of AY and BY. To do that, we have three equilibrium equations available to us. And those equations are summation forces in the x direction is equal to 0, summation forces in the y direction is equal to 0, and summation moments is equal to 0. Let's go and look at the calculation for AY and BY. Okay, I have placed on the simple beam I've placed a point load representing the UDL, or the uniformly distributed load. We know that every meter that we go over, or on the base of it, on the width of it, every meter is going to be 7 kilonewtons. So we have 2 meters here. 7 times 2 is 14. I'm going to put it through the centroid of that particular UDL. Okay? It will help me with my calculation. It is not part of the FBD. It just helped me with my calculation. I'm going to do moments about point A. It'll eliminate the most amount of unknown force at that point. And I'm going to have a moment that's created by the UDL. I'm going to have a moment that's created by the point force. And I'm going to have a moment that is created by the reactant at B. Okay, so we're going to have 3 moments. We're going to have 3 sets of terms. Terms are separated by minus and plus signs. So we're going to have 3 sets. The equation is summation moments about point A is equal to 0, and counterclockwise rotation is considered to be positive. That's what that is telling us. Okay, let's go and create the magnitude. Remember that a moment is force times perpendicular distance, right? So we have the magnitude of the force right there, 7 times 2, which is 14, times the perpendicular distance. Well, that perpendicular distance happens to be through the centroid of that shape, so that will be 2 divided by 2, which will give you 1. We can't forget, I should say, that the rotation is negative. This is going to create a negative rotation about point A, so therefore we have a minus right in front here. When we look at the point load right here, again we have a negative rotation. It's going clockwise. And we have a perpendicular distance to that line of action. That line of action is 2 plus 3, which will give you 5. So minus 12 times 5 will give you minus 60. We also have a moment that's going to be created by By here. It's going to go that direction. And that particular moment has a perpendicular distance of 2, 5, 9. So 9 times By in the positive direction. When you crunch those numbers, you're going to have 8.222 kilonewton as your reactant force. Okay, 8.222. I have carried an extra digit here because my final answer I round off to 3 sig figs. The intermediate answers I just keep a guard digit so that I have accurate answers. Okay, this force, when I write a force, I have the magnitude. We have all 4 components of a force. Magnitude, the direction is vertical, the sense is up, and point of application is point B. So we have magnitude, direction, sense, point of application. Okay, let's go and calculate the force for AY now. I cannot reuse my equilibrium equation for one scenario. Okay, I cannot reuse the equilibrium. I've done summation moments. I cannot use summation moments about point B and solve for AY. I have to choose one of the other 2 equilibrium equation, and the appropriate equation to choose is summation forces in the y direction is equal to 0, and of course we have going up is positive. Okay, going up is positive. When we look at forces going up, we have AY going up, that's a positive. We have the 14 kilonewton going down, which is a negative, and we have 12 kilonewton going down, a negative again, and we have a value, a magnitude for By now, and that's going up, positive. Crunch the numbers, you have 1778 kilonewtons acting up. So now we have all of our magnitudes that we need for FBD. Okay. Again, my final answer, I'll run off the 3 significant digits. The other answers, I'm going to carry a guard digit. Let's go and construct a deflected shape diagram now. Okay. The deflected shape diagram is constructed from the beam diagram. It is the red line here showing the way that the beam would actually deflect under loading. Okay, it's a bit exaggerated for demonstration purposes, but it is the way that the beam, the shape that the beam would actually take under loading. So this is it right there. We have a beam that's pinned at two locations, and it has forces acting down in between those two locations. It will cause this type of shape. On the upper part I have a C, and the lower part I have a T. The C represents compression, the T represents tension. Now let's consider a wooden beam. Okay, if I were to take one fiber on the upper half of the wooden beam, a fiber right there, for it to assume the shape, what has to happen to that fiber, it has to be compressed. So the forces must be acting towards the member. The member is being the fiber now. And when you look at the lower half of the beam, the fiber has to be stretched. So the force has to be acting away. It has to pull it apart to stretch it. And anytime that we have forces acting towards a member, it is compression, and force acting away from the member is tension. Okay, so that's how we decide which side is tension and compression. Also, the dotted line could be considered the neutral axis, which you don't have any tension or compression there. That's a separating line between tension and compression. Okay, so you could consider it the neutral axis in that respect. So we have a deflected shape. One other thing about the deflected shape, the internal moment in the beam always act, if you were to put a moment, it's more like a torque, it's a rotation. You would put the arrowhead towards compression. It depends on where you cut the beam. Okay, the open end is where the moment will bleed out. Let's go and look at the load diagram. The one thing that you have to remember about the load diagram, all positive force, which are forces acting up, goes above your datum line. The datum line is right there again. It is the darker black line. All forces from your shear force diagram that's acting up will go above. All forces acting down will go below the datum. And that's the only thing that you have to remember. If we were to look at our forces, we have the reactant AY acting up. I placed it above the datum. I have the UDL right there, uniformly distributed load, right across that area. It is a negative load. It's acting down. Okay, so I put it below my datum. I have my point load right there, and that's acting down below, and then the final one, BY, acting up. I've replaced the actual labels of the reactants with the actual magnitude or the values of them, so I don't need to maintain the labels at this point. Okay, that's all there is to a load diagram. As you could see, we went from the beam diagram to the free body diagram. We needed the beam diagram, the information from there to actually draw the free body diagram. Then we went to the load diagram also. We needed the information from the free body diagram to draw the load diagram. Okay, let's go and construct our shear force diagram now. And when we look at the shear force diagram, fairly simple concept again. We're going to start from left going to the right side, and we're going to use the load diagram to construct it. We have the load diagram here. We're going to start from left again. We are increased by 1778 right at that point. So I have a direct increase of 1778 kilonewtons. Between this point and this point right here, between the left side and the end of the UDL, I have a uniformly distributed load. So it's nice and even. It's going to be a straight line section. However, as you go from left to right, it's increasing, so it is going to be a decreasing situation here. Okay, you're going to go from 17.78 kilonewton, you're going to reduce by 14 kilonewton, which is the total magnitude of that. So you're going to go down to 3.78. I'm going to just take 14 away from 17.78. I'm going to get 3.78 right at that point. Okay. From that point, if I were to look at my load diagram, from this point here, there's no influence. There is no influence until we get to the 12 kilonewton force. So then on my shear force diagram, that remains constant. It remains a horizontal line. And then when it gets to this point here, it's influenced by the 12 kilonewton force, which knocks it down to the negative side, actually. I'm going to take 3.78 minus 12. I'm going to get minus 8.222. Okay, so I've gone to the negative side of the shear force diagram. I'm not going to be influenced by any force in between here until I get to the end. So I stay constant, and then when I get to the end, I'm bumped up by 8.22. And this is important. We started at 0 and we ended at 0. We could feel fairly confident that we have actually done whatever is done in here well. So we close, we have a check. Okay? It doesn't mean that the moment diagram is going to check. If the moment diagram does not close to 0, that means that our reactants are calculated incorrectly. Okay? The next thing, before we could go and construct our bending moment diagram, we have to calculate the area under the shear force diagram, and that area represents a moment. Okay? When we look at force times distance, that would be a moment. In this first area here, we have a trapezoid. We have a base, two parallel bases right there, and we have a distance in between them. So I'm going to calculate that area with the trapezoid formula. 17.78 plus 3.78 divided by 2, which is the average of the base, times the distance between them, the two bases, which is 2 meters. So you don't see the 2 meters very well here, but when you crunch the numbers, it equals to 2156. And that would be kilonewton meter. So you have gone from force times distance, kilonewton meter. So the area under the shear force diagram is a moment. And in this case, it's a positive moment. Let's go and look at the rectangular shape now. We have 3.78 right at that point. We have a distance of 3 meters. So 3.78 kilonewton times 3 meters will give you 1134 kilonewton meter. Again, a positive moment. Okay? When we look at the last rectangle that we have here, the last rectangle, it is a minus rectangle because we have a minus force and we have a distance of 4. So to calculate that will be minus 8.22 kilonewton times 4 meters will give you 32 or minus 32.88 kilonewton meter. Okay? That's the number right in there. So we have all the information that we need for constructing the bending moment diagram. The other thing that we have to remember, when we have rectangles on the shear force diagram, which we have 1 and 2, those are straight line on the bending moment diagram. When we have triangles or trapezoid, which we do have here, that's going to be a curve. But there's different curves. If you have different orientation of the triangle, it represents a different type of curve. If you have a negative area or a negative moment, that's a different type of curve. You have a concave and convex curve that happens with that. And I'll show you a fairly easy way to remember these curves. All right? Let's go and look at the Kahn's bending moment bug. You won't find this in any textbook. Okay? It gives the shape of the curve for the bending moment diagram for triangles and trapezoids. So it gives the shape of the bending moment diagram. These are the shapes that I'm speaking about, these curves here for triangles and trapezoid. The shape of the shear force diagram for triangles and trapezoids are converted into curves on the bending moment diagram. So when we look at this, we have a diamond really, and it's separated into 4 equal parts. We have the upper part of the diamond are represented by areas of triangles, and those are positive area. The lower part of this is negative area. As you could see, for the positive areas, we have here, depending on the orientation of the area, we have here a concave rising up. Okay, it's rising. For the other positive orientation, we have a convex rising up. Convex rising up. When we look at the negative areas, for the first orientation that we have here, we have a convex falling. And for the next one, we have a concave falling. Okay, so these fairly simple way to remember this when you are on evaluations and stuff like that, and you need to remember these shape. It's just a bug. It's separated into 4. You start from the left hand side, you have the whisker of the bug, and you have the back leg of the bug. Okay, fairly easy. Let's go and construct our bending moment diagram now. I've placed the bug right at that location. You don't have to do this on your work. This is just for me to get the appropriate shape for this particular trapezoid shape when I do the bending moment diagram. As you could see, we know that we're going to have a curve right in there. My triangle is positive, first of all. It's a positive moment. And I have an orientation where my right angle is right there. That is the shape that I'm looking for right there. So I know I have a convex rising. A convex rising. How much is it going to rise from 0? The amount of the moment, right? So I'm going to put my moment right there. I'm going to draw a convex rising up to it. The next shape that comes into play happens to be a rectangle, and that again is a positive moment. It's a positive moment. It's 11.34 kilonewton meter. From my 2156, I'm going to rise again, and when I add those two numbers, I'm going to get 3278 kilonewton meter. Okay. From that point, I have a negative moment, and that negative moment happens to be exactly matching what my magnitude here is, which is positive. So I know I'm going to go back to 0, and because it's a rectangle, I am going to go in a straight line to 0. I could feel now confident that all my work that I've done previously is correct. Everything is going very well. Let's go and pick out our Vmax and our Mmax. Vmax is the maximum shear force, and I'm going to round my final answer off to 3 significant digits. When I look at how to pick off my Vmax, it's the maximum deviation from my datum. Maximum deviation from my datum. Okay, whether it's positive, in this case it is positive, or negative. I'm going to record it as an absolute value number, 17.8 kilonewtons. Okay. Again, the same rules apply to the bending moment diagram. The maximum deviation. If this was happened to be in the minus sign or the minus side, then I would just record it as a positive again. And that maximum deviation, you could see it right there, 32.8 it becomes kilonewton meter. Okay. This is all that I have for you, and I hope that it explains how to construct the shear force and bending moment diagram. Have fun with it. Bye-bye.